each end. When the train is at the middle of the train, the detector is closest to Sue. These two lights here will flash. The one on the right will flash in all directions. The one on the left will flash in all directions. Sue's got her meter there, and she notices that they do indeed flash at the exact same time because the two lights get to her at the exact same time. We're assuming that there is no interference of anything in the air. Just let's not worry about refraction in the air. So Sue sees that the two lights go off at identical times, exact same time. Now, if the right light gets to the detector first, the detector is going to glow green. So detector will be green if right light gets there first. The detector will be red if the left light gets there first. Or left and right light get there at the same time. So the two lights go off. Sue sees the two lights go off at the same time. The car then passes by. The detector in the middle is either going to glow green or glow red. There's really no other option. And so then they stop the train car and they look, and the light is green. So from that argument there is that the two lights go off. The light waves are coming towards the detector, but the detector is moving this way. The detector is moving closer to this light right here. And so this light's going to get there first. So Sue says, yeah, I expect it to be green. Lou, on the other hand, says, wait a second. Both of those lights and the detector are all at rest relative to me. Because Lou's right there in the car, on the car. If those lights go off at the exact same time, those two lights should get to the detector at the exact same time. It should glow red. But when they stop it, it is green. Lou's analysis seems to have a flaw in it. Actually, the way I worded it was correct. There's a flaw in an assumption. How can that be? What's wrong with Lou's argument? Assume the detector works properly. And Sue has confirmed that the lights go off at the exact same time.
Lou's not considering that she's also moving at the same speed of the cart.
Yeah, but from his point of view, he's at rest relative to the cart. Sue's coming at him, going that direction, at however fast the cart was going relative to Sue.
If she was going that direction, then she would encounter the light on the right first.
So you're saying she would encounter the light on the left first?
Yeah, it would be in line first.
If they went off at the same time relative to Lou, then yes, Sue would detect differences there. But she doesn't.
So I guess Sue is more right again on the more still or whatever relative to Luke.
No. All right, let's say there's a light smack dab in the middle of the room. I have two lights on both sides. So, detector perfectly aligned in the middle, two lights equidistant from the detector. If the lights go off at the same time, they're going to both get to the detector at the same time. I'm ignoring assumed flat Earth, Earth doesn't rotate. Is there anything wrong with that?
No.
Okay. Now, if I had, again, two lights detector, if I said that the light on, I do it from your point of view, the light on the right gets there first, what would you conclude?
That we're moving.
No, I mean, they're still at rest relative to us.
I mean, the Earth is moving.
They're still at rest relative to us.
That the detector is closer to the right than the left.
No, already confirmed that it is perfectly aligned. The detector in the middle is the exact same distance from both lights. And I'm saying the light right gets there first.
The right is faster.
Say it again?
The right light would be faster.
No, light's still at the same speed for both of them.
I mean, is everything moving relative to whatever's light's absolute speed?
We are all at rest relative to each other. The two lights are at rest relative to you. The detector in the middle is at rest relative to the lights and to you. It is all perfectly still, except for the flash of light. It's that leap of faith. Remember, we're talking relativistic effects here. All right. Let's say that Patrick and Sarah live at same distance from the school. And we've done the tests. We know that it takes them the exact same amount of time for them to get from home to school. Same distance, same speed. Sarah gets there first. How is that possible?
Traffic.
Same distance, same speed. Let me set it up again just in case I misspoke. Patrick and Sarah live the same distance from school. It takes them the exact same amount of time to get there. Sarah gets there first.
So there's some sort of time dilation or something.
No, no time dilation. We're talking everyday life. Same speed, the time dilation will be the same for both of you. How could one person get to school before another person if it takes them the same amount of time?
Did they leave earlier?
Yes. Back to here. How could, if the two lights are at rest relative to Luke, how could the right light get to them first?
It flashed first.
Yes. But Sue said that they flash at the exact same time. So from Sue's point of view, they do flash at the exact same time. From Lou's point of view, they don't. Just because two things happened at the same time in one reference frame does not mean they happened at the exact same time in another reference frame. That gets into some really funky things. So now it's a question of how much math I subject you to. And I'm inclined to get you more math than I did for 152. Assuming that I find that sheet. So why don't we take a break here, stretch legs. We'll come back and we will talk about how do you actually translate between when the location and time of one event translates to the location and time in a different reference frame. Let's do some math. Woo! Just suppose I have a light pulse. So something flashes, light goes out in every direction, and so basically the radius of this burst of light would be just the speed of light times however much time passed. So I could write an equation for this sphere of light, or at least this one burst of light, that x squared plus y squared plus z squared is equal to ct squared. Now, if I am moving, so this burst of light goes off and I am in a moving reference frame, so I'm in a primed frame. Well, from that point of view, speed of light is the same, and so x prime squared plus y prime squared plus z prime squared should be equal to ct prime squared. Well, if I want to translate between the two, let's think about if you are you're in a car passing through an intersection, and as you pass through the intersection, the time from a bystander and the time of you in the car are synchronized. There's another light over here, a distance x away. When you have gotten to this point right here, the light changes to red. The distance you have traveled at that point is vt. This distance right here would be the distance from you to the red light, and so x prime. So from the car's point of view, the light turns red when it is x prime away, and from bystander of the previous light, it's the distance x away. So we have this relationship that x is equal to x prime plus vt, comparing the two reference frames, or x prime is equal to x minus vt. This is Galilean relativity. I'm going to take my x minus vt and I am going to plug that in for x prime. I'm assuming there's no change in y or z, so formally y equals y prime and z equals z prime. So I plug x minus vt in for x prime, and I get x minus vt squared plus y squared plus z squared is equal to ct squared. Again, assuming non-special relativity. We end up with x squared minus 2vt plus v squared t squared plus y squared plus z squared is equal to c squared t squared. Now for the other reference frame, I've got my x squared plus y squared plus z squared is equal to c squared t squared. If I subtract the two, I end up with negative 2vt plus v squared t squared is equal to 0. If that's the case, v squared t squared is equal to 2vt. One of the t's cancels out, one of the v's cancels out, and I'm left with vt is equal to 2. So if the speed times time is always equal to 2, then Galilean relativity works. But I think you both know that you can take your speed, multiply it times time, it's not always going to equal 2 in whatever units it happens to be. I guess it would be, well, whatever units. So what this whole point of this is to show is that Galilean relativity is not sufficient. So we need to somehow come out with something that is sufficient. And so let's begin our math journey. Oh, I did leave something off there. I thought something was odd. There should be an X in there. X. 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 Okay. 2 is just the number 2. Still, Galilean relativity is not sufficient. All right, so we're going to work under this assumption that we're dealing with non-accelerating frames. So if I have an object going from this point to this point, then I'm going to assume that no matter how fast I'm going, it's still going to be a straight line. That there's no curving to it unless there's acceleration going on somewhere. So the relationship between the prime frame and the x frame's got to be linear, and so we have x prime is equal to, we'll just say a1x plus a1t, and that y, not y, and t prime is equal to b1x plus b2t. There's some linear relationship between the two position and times. I am also going to work under the assumption that y prime equals y and z prime equals z. In other words, we're moving in the x direction. And if you're thinking, wait a second, how do we deal with those other problems? Well, we can always change our reference frame so we're always moving in the direction of whatever the event is. All right, so the origin in the prime frame is whatever, in the case over there, a car. We can think rocket also if you wanted to. So in the S prime frame, and I'm going to draw it more traditionally over there. So that was our starting point. Let's now. Here's my S frame, and then I have an S prime frame traveling at some speed with, so the speed of S prime with respect to S is just equal to V. when x prime equals 0 and x equals 0, we synchronize the times. So as this is passing through, we synchronize it when s prime is basically right there. So at this point right here this would be x prime, and that would be x. X prime, not x subscript 1, x prime. So when x prime and x are both 0, we synchronize the clocks. I know also that at some time t, so again from the s prime, from the s frame, at some time t, s prime has moved, so this is from the s point of view. S prime is at the position vt. It's how fast that the thing is going relative to Earth, or relative to s, times however much time has passed in the s frame. So from that, well, from the s prime frame, you're at position 0, plus a1x plus, ooh, that should be a2 there. a2 times time. And I'm going to rewrite that because there are several mistakes in that. 0 equals a1 times vt plus, oh, remember that also, plus a2 times t. So a1 vt is equal to negative a2t. The times cancel out. And so my speed is going to be, whatever my speed is, it's going to be the ratio of negative a2 over a1. So there's two coefficients. What we're trying to do is figure out what a1, a2, b1, and b2 are. And so our first step is we can now simplify it some.